All right, welcome back, everyone. Tonight we're going to take a look at half-life. Now, in your reading of Chapter 18, as well as the nuclear science video lecture that we watched in class, we learned that half-life is the time required for half of a sample of radioactive material to decay. What we didn't really look into in the book or in the video was exactly how half-life is calculated and what kind of a process this is. Half-life is not a linear process. It's something called exponential decay. If you take a look at the graph on the bottom right-hand corner here, this shows you the exponential decay or half-life of carbon-14. The number of half-lives can be calculated by counting how many times a 10-gram sample of carbon-14 decays by 1/2. If we start taking a look here at starting with 100% of 10 grams at time 0, this is a full value of our starting value of carbon-14. After one half-life, which is 5,730 years, after one half-life, we're down to 50%, which is 5 grams. After the second half-life, we're half of 5 grams. We are at 2.5 grams, or 25% of the original mass. After the third half-life, we're at 12.5% of the original mass, and we're at 1.25 grams. We can continue to divide by 2 every single half-life, and technically you never actually hit 0. That's something pretty important when you get to Algebra 2 and you start learning about exponential decay. Okay, let's go to the next slide for our example for the night, and then we're all done. Okay, of course, like usual, I want you to pause the tape and copy down the entire example for tonight. All right, I hope you got it down. Here's a typical example that we may run into with half-life problems. An isotope of cesium-137 has a half-life of 30 years. If 100 grams of cesium-137 disintegrates over a period of 90 years, how many grams of cesium-137 will remain? Now, when you get to Algebra 2, you'll learn about something called, as usual, I want you to pause the tape and copy down the example problem in its entirety for your notes. It does not help you to watch this video and simply copy down the solution. You have to know the problem, guys. Please stop now. Okay, I'm assuming you listened to me and you've got this problem down in your notebook. Let's take a look. We have this isotope of cesium-137. It has a half-life of 30 years. If a 100-gram sample of cesium-137 disintegrates over a period of 90 years, how many grams of cesium-137 will remain? Well, our first order of work here is to figure out how many half-lives we have gone through for a period of 90 years. So the one thing we need to take a look at is where we can do some converting. If a half-life is equal to 30 years, we have an equality. One half-life equals 30 years. So we can literally use dimensional analysis to convert 90 years into half-lives. So 90 years, we want to get rid of years, so we're going to put 30 years on the bottom and one half-life on top. When we do that, we find out that this particular sample of cesium-137 has undergone 3 half-lives. Now it becomes a T-chart situation. If you draw a little T-chart for time and half-lives, half-lives and amount of sample, okay, At 0 half-lives, which is times 0, we're starting with 100 grams of sample, and that's in grams. After 1 half-life, half of that sample remains. Well, what's 100 divided by 2? You're right, 50. Remember sig figs. After the second half-life, half of 50 is left, or 25 grams. That's 1/4 of the original sample. After 3 half-lives, we need to see that we have half of 25. Half of 25 is 12.5 grams. So we can finalize our answer and say, let's see here, let's change the color for us. After 90 years, 12.5 grams of cesium-137 will remain from the 100-gram sample. And that's it. We're done. That's your example. Have a great night. Be ready to do some problems tomorrow.